fourth normal form talks about the multivalued dependency. What multivalued dependency is? That if there is a functional dependency which a single functional dependency is deriving, or single attribute is deriving different attributes, so it should be removed. That is multivalued dependency. And the five normal forms said about the lossless decomposition or joint dependency. You should remove the lossless decomposition or a joint dependency. So lossless decomposition we can say, or a joint dependency. The domain key normal form is not, actually this two normal form is of no practical use. We are concentrating up to four normal forms. The first normal form says that the value should be atomic. Second normal form says that there should not be a partial dependency. Third normal form talks about the transitivity dependency. BCNF, that is Boise code normal form, talks about overlapping candidate keys, and fourth normal form talked about a multivalued dependency. Okay, so in practical these four are important. In gate examination the questions might be asked that every relation which is in a three normal form is also in a two normal form. Every relation which is in a four normal form, it is also in a DKNF. So you have to remember this hierarchy so that you can conclude which one is the correct option. Now let us take an example. The relation is given on the key values or attributes A, B, C, D, E, F, G, H, and the functional dependencies are also given. Now here we see that the key is already given, or you can find out the key by using closure set of attributes, as we have seen in a previous videos how to find out the key for a given relation. Okay, so here we have already find out the key, that is A, B. The given relation is already in a 1NF form, so what we are going to convert it in a 2 normal form. Now to find the tables in a 2 normal form or a relations in a 2 normal form, first we have to find out the closure of A and the closure of B. Why we are finding the closure of A and B? Because they are the elements or attributes of our key. So try to find out the closure of A. So closure of A, how to find out the closure we have already seen in the previous videos. First match the left hand side and whatever they are on the right hand side, add it. So the closure will contain AD only. Then the closure of B first B itself. Then that's it. So in A we are having just AD, and in B we are having just B. So from that we can say that the relation 1 is going to have A and D, whereas relation 2 is going to have A, B, C, E, F and G, H. Okay, so whatever the remaining keys, that all are included in a second relation, because in B we can see there is no other attributes. Okay, now this is our tables in a 2 normal form. Now I have to convert it in a 3 normal form so that there should not be any transitive dependency. Okay, now if you see, AD is a separate, so it is don't have any transitivity dependency. But if we see in relation 2, there are a transitive dependency. For example, we can say that F tends to G, and we are also having AB tends to F. If you see here, AB tends to F and F tends to G, so indirectly AB tends to G. So that becomes the transitivity dependency. See over here, AB tends to F, F tends to D, which implies AB tends to G. So this is the transitivity dependency, so we have to remove it. So in relation R there is no change, so it will remain as it is. But in relation 2 we are having a problem, so we will split in a R2 and R3. So we will keep FG separate, and whatever is remaining we will keep it in a one table. Okay, now if you see over here, there is no transitivity dependency, as we have removed FG, which creates the transitivity dependency. Okay, now this is in a 3 normal form, we are having 3 tables. Now if I want to convert it in a BCNF, as you see that after 3NF we are having BCNF, and most of the time 4NF, 5NF and DNF, these 3 are of no practical use, so we will going to convert up to BCNF only. Now see, most of the time whatever the relation is there in a 3NF, is already equivalent to in a B, C and F if you are having a single attribute value as a key. But as we are having three relation, we have to check whether our 3 and F is already in a B, C and F or not. So we have to remove the candidate keys. So what we are going to do over here, we are going to write down the keys and the determinant. If you remember about the determinant, whatever the present on the left hand side of a functional dependency is called as a determinant. So first we will write whatever there on the left hand side of a functional dependency as determinant. Now we have to write down the keys. The keys are taken from a 3NF form. Whatever the keys are there in a 3NF, that will be written as it is. So A, F and AB. So these are the keys for this table. These relations are nothing but three tables, and each table is having its primary key like A, F and AB. Now say these three are equivalent, so we don't have to think about this. If all the determinants are keys in 3NF, then we can directly say that 3NF is already in a BCNF. But if you see over here, we are having three extra determinants over here, so we have to check whether these determinants are a candidate keys or not. Okay, if they are a candidate keys, then it is okay, but if they are not a candidate key, then we have to split that table and increase the number of tables in our keyword relation. Okay, so first thing that we have to check is whether these three are the candidate key or not. Now let us check whether they are a candidate key or not. So to check whether they are a candidate key or not, we have to simply take the positive closure or a closure set of that attributes. In closure set, you remember that we include the relation, that is for whom we are finding the closure. So HBC includes ADEFG. Now if you see A, B, C, D, E, F, G, H all are included, if your attribute or a closure set contains all the attributes of your relation, then this can act as your candidate key. Then after that, FBC. In FBC determines A, D, E. Then FP determined H. FB determines H. Now who is remaining? A, B, C, D, E, F. Only G is remaining. If you see, single F is finding G, so G also included. So this can be also a candidate key. So we don't have to think about HBC and FBC. Now let us take off FB. From FB, H and G can be derived. From FB, H, from FG can be derived. Now, what about the other attributes? From FB, H, G, other attributes cannot be derived, so it cannot be a candidate key. As it is not a candidate key, we have to split this table which is having FB. Okay, so what we are going to do is, how we are going to convert this table is, we are going to keep FB in a separate table with its determinant. As FB doesn't have a candidate key, we are going to keep it in a separate table. Now our two table is remain as it is, that is AD and FG. We are not going to do anything with AD and FG. Now what we are going to do is, we are adding another table which is having FB and the what it is deriving is H. Now we have to remove this H from this table because we have already included H in this table. So what is remaining in this table is A, B, C, E, F. We are just removing the H from this table. Okay. So in BCNF, what we are having over here, F, B, H and A, B, C, E, F. And the remaining two table AD and FG is as it is. Okay. So this is how we have removed or we have converted the given table in 2NF, 3NF and BCNF. Hope you have understood the concept of normalization and how to convert the given set into this normalization. Thank you.